When we left the story, Earth had just survived the most violent event of its short life. A body the size of Mars had struck it, blasted a portion of itself into orbit, and left behind a glowing companion in the sky. You might reasonably assume that after a collision of that magnitude, things would settle down. They did not. What followed the moon's birth was not a period of healing. It was, if anything, a continuation of the same violence, stretched out across 500 million more years. This is the story of the Earth that existed after its core had formed, after its moon had risen, and long before it had anything resembling the planet we would recognize today. This is the story of the violent young Earth. Geologists refer to this earliest chapter of Earth's history as the Hadean Eon, a name deliberately borrowed from Hades, the underworld of Greek mythology. It is by design not a flattering name. The Hadean spans from Earth's formation around 4.54 billion years ago to roughly 4.0 billion years ago. We spent the last episode inside its earliest chapter. This episode covers what came after. A world still being struck, still glowing, still fundamentally unfit for anything we would call life. To understand just how hostile this period was, it helps to understand what Earth did not yet have. It did not yet have a stable, calm ocean sitting quietly on its surface. It did not yet have a breathable atmosphere. It did not yet have plate tectonics operating in anything like its modern form, and whether it had any form of tectonic activity at all during this period remains an active area of scientific investigation. What it did have in abundance was heat, poison gas, and falling rock. If you could have stood on Earth's surface during much of the Hadean, an impossibility since there was no breathable air and almost nowhere solid or cool enough to stand, you would have witnessed something that looked less like a planet settling into adulthood and more like a battlefield that refused to fall quiet. Debris left over from the solar system's violent formation was still everywhere. Asteroids and smaller planetesimals, the leftover rubble from the accretion process we described in the last episode, continued to rain down onto every rocky surface in the inner solar system, Earth included. For decades, scientists have debated whether this bombardment was simply a slow, steady decline from the chaos of planetary formation, or whether it included a distinct, dramatic spike in impacts, a second, more concentrated wave of destruction arriving hundreds of millions of years after Earth and the Moon had already formed. That hypothesized spike has a name, the Late Heavy Bombardment, sometimes called the lunar cataclysm. We will look closely at the evidence for and the ongoing debate about that specific spike shortly. But regardless of whether the bombardment arrived as a steady decline or a dramatic renewed wave, one fact is not seriously disputed. Throughout the Hadean, Earth's surface was struck by far more debris, far more often than it is today. Here we run into the same problem we encountered when dating Earth's birth. Our planet's own surface has erased almost all direct evidence of this period. Billions of years of volcanism, tectonic activity, and erosion have destroyed the Hadean crust, recycling it back into the planet. Once again, the moon comes to our rescue. Unlike Earth, the moon has no atmosphere, no oceans, no plate tectonics, and essentially no erosion. Craters formed billions of years ago remain largely as they were the day they formed, making the moon something close to a fossilized record of the early solar system's violence. When the Apollo missions returned lunar samples between 1969 and 1972, scientists were able to radiometrically date the ages of impact melts, rock that had been melted by the heat of ancient collisions and then solidified again. A striking pattern emerged in several of these samples. An unusually large number of them appeared to date to a relatively narrow window, clustering around 3.9 to 4.0 billion years ago, rather than being spread evenly across the moon's entire history. This clustering is what led to the Late Heavy Bombardment hypothesis. The idea that roughly 500 to 600 million years after the solar system formed, the inner planets experienced a sudden, sharply elevated wave of impacts, potentially delivering more material to the inner solar system in a relatively short window than had arrived in the hundreds of millions of years before it. Some of the Moon's largest and most recognizable features are thought to be scars from this very period. Basins such as Imbrium and Nectaris, vast impact craters later flooded by dark lava to form the shapes we now casually call the Man in the Moon, are estimated by many researchers to date from this same general window of intense bombardment. If Earth experienced anything like the pattern seen on the Moon, and given its far larger size and gravitational pull, Earth would likely have been struck by significantly more material than its smaller neighbor. This would have meant a planet subjected to repeated large-scale impact events long after its initial formation was supposedly complete. A spike in impacts demands an explanation. What could have disturbed the outer solar system's leftover debris hundreds of millions of years after the planets had already formed and presumably settled into stable orbits? The leading dynamical explanation is a body of work generally referred to as the Nice model, named for the French city where the research group that developed it is based. According to this model, the giant planets, Jupiter, Saturn, Uranus, and Neptune, did not form in the exact orbits they occupy today. Instead, computer simulations suggest they originally formed closer together in a more compact configuration, surrounded by a massive outer disk of icy planetesimals extending well beyond Neptune's current orbit. Over tens or hundreds of millions of years, gravitational interactions between these giant planets and the surrounding disk of debris are thought to have caused them to slowly migrate, Jupiter drifting slightly inward, while Saturn, Uranus, and Neptune drifted significantly outward. At some point in this migration, the model proposes, Jupiter and Saturn crossed a specific orbital resonance, a ratio of their orbital periods that amplified their gravitational influence on everything around them. That resonance crossing is thought to have gravitationally destabilized the surrounding disk of icy debris almost instantaneously, scattering enormous numbers of comets and asteroids in every direction, some flung outward to form structures like the Oort cloud, and a significant fraction sent plunging inward toward the inner solar system, where Earth, the Moon, Mars, and Mercury waited. It is worth being clear about the scientific status of this model. The Nice model is a leading, well-developed dynamical hypothesis that successfully explains several otherwise puzzling features of our solar system's current architecture. Not only the possible bombardment spike, but also the present orbital positions of the giant planets and the structure of the Kuiper Belt. But it remains a model under active refinement, with newer variations, sometimes called the Nice 2 model, continuing to adjust its specific details. Bombardment from above was only part of what made this era so hostile. Beneath the surface, Earth's own internal heat was doing plenty of damage on its own. Recall from the last episode that Earth's interior, during and immediately after its formation, had separated into a metallic core and a rocky mantle through a process driven by intense internal heat. That heat did not simply vanish once differentiation was complete. Radioactive decay of elements like uranium, thorium, and potassium continued generating heat within the mantle, while the mantle itself remained hot enough and fluid enough to convect, slowly churning like an extremely viscous, extremely hot fluid. That churning mantle needed somewhere to release its heat, and it did so through relentless volcanic activity. Rather than a small number of isolated volcanoes, as we tend to picture today, the Hadean Earth is thought to have had extensive regions of active or recently active volcanism across much of its surface, continuously resurfacing the planet with fresh lava. Combined with the continuing bombardment from above, this meant Earth's surface during much of the Hadean was in a near constant state of renewal through destruction. Freshly solidified crust could be melted again by a nearby volcanic eruption, or simply blasted apart by the next incoming impactor, only to cool and solidify once more, briefly, before the cycle repeated. Whether Earth had anything resembling plate tectonics, the process by which large plates of solid crust slide over the mantle, colliding and separating, that shapes our planet's geology today, during this period remains genuinely unresolved. Some researchers argue for an early, more primitive form of crustal movement even in the Hadean. Others argue true plate tectonics did not begin until significantly later. What is generally agreed upon is that whatever form it took, Earth's surface during this period was neither stable nor calm. If the ground offered no rest, the air offered no relief either. Earth's earliest atmosphere formed through outgassing, volcanic eruptions releasing gases that had been trapped within the planet's interior since its formation, along with contributions from the steady rain of comets and asteroids, many of which carried volatile compounds of their own. The dominant gases in this atmosphere are generally reconstructed as carbon dioxide and nitrogen, with meaningful quantities of water vapor, released continuously by ongoing volcanic activity. Smaller but scientifically significant quantities of other gases were likely present as well, including methane and hydrogen, potentially produced both by volcanic outgassing and by chemical reactions between certain iron-rich minerals and water at depth, a process called serpentinization. There was notably essentially no free oxygen. The oxygen-rich atmosphere we breathe today is a much later development in Earth's story, arriving only after photosynthetic life had existed for a very long time, an event we will cover in detail several episodes from now. During the Hadean, an atmosphere thick with carbon dioxide, along with whatever methane was present, would likely have produced a substantial greenhouse effect, trapping heat and helping keep surface temperatures elevated even as the young sun itself was notably dimmer than it is today, by perhaps 25 to 30%. That last detail is worth sitting with. The sun that shone faintly on this scarred and glowing planet was not the same sun we see today. Younger stars like our early sun are less luminous, a well-established consequence of stellar physics as a star gradually brightens over billions of years of hydrogen fusion. Without a correspondingly strong greenhouse effect from gases like carbon dioxide and methane, models suggest Earth's surface could plausibly have frozen solid despite its ongoing volcanic heat, an apparent contradiction with other geological evidence that has never fully frozen over that planetary scientists refer to as the faint young sun paradox, and one still actively studied today. Beyond its chemistry, this atmosphere was almost certainly thick with ash and dust, kicked up by continuous volcanic eruptions and impact events, at times likely obscuring the sky for extended stretches. Between the toxic gas composition and the airborne debris, this was an atmosphere that offered no shelter and no relief, as hostile in its own way as the ground below it. Science does not deal in tidy, uncontested stories, and it is worth pausing here honestly on a genuine and ongoing debate. The Late Heavy Bombardment hypothesis in its classic form, a short, sharp spike of impacts specifically concentrated around 3.9 billion years ago, has faced serious challenges in recent years. Some researchers have argued that the apparent clustering of ages in the Apollo samples may be a statistical illusion, caused not by a genuine spike in bombardment, but by sampling bias. Many of the Apollo landing sites were chosen specifically near one particular ancient impact basin, called Imbrium, whose ejecta may have contaminated and reset the ages of rocks across a wide area, making one enormous singular event look in the data like many separate impacts spread across a narrow window. Other researchers have proposed a middle position, that the bombardment rate did decline fairly steadily from the earliest, most chaotic days of planet formation, without a distinct secondary spike, but that it nonetheless remains significantly elevated compared to today for a very long stretch of the Hadean and early Archean. This matters for our story, but perhaps less than it might first seem. Whether the bombardment arrived as one dramatic, concentrated cataclysm around 3.9 billion years ago, or as an extended, gradually declining hail of debris stretching across hundreds of millions of years, the practical result for Hadean Earth was broadly similar. A surface struck far more frequently, and often far more violently, than anything we experience today. At a scale capable of vaporizing entire ancient oceans in the largest individual events, according to some models of the biggest hypothesized impacts of this era. What this debate really illustrates is something worth appreciating about science itself. The story of Earth's violent youth is not delivered to us complete and finished. It is actively being investigated, revised, and argued over by scientists working with genuinely difficult, ambiguous, billions of years old evidence. Amid all of this violence, there is one genuinely surprising thread of evidence worth mentioning before we close this chapter, because it complicates the picture in an interesting way. We mentioned in the last episode the tiny zircon crystals from the Jack Hills region of Western Australia, the oldest known individual minerals on Earth, dated to as much as 4.4 billion years old. These crystals do more than simply mark a date. Their internal oxygen isotope ratios have been studied closely by geochemists, and several research teams have argued that those ratios are consistent with the crystals having formed in the presence of liquid water, at relatively low temperatures, rather than in a completely dry, molten hellscape. This has led some scientists to propose what is sometimes called the cool early Earth hypothesis. The idea that, even amid the broader violence of the Hadean, Earth may have had at least localized, temporary periods in localized regions cool enough to support pockets of liquid water on its surface, considerably earlier than the more dramatic, fully molten picture might suggest. This hypothesis remains genuinely debated, and it does not overturn the broader picture of a violently bombarded, volcanically active young Earth that this episode has described. Rather, it's a reminder that even our most violent chapters likely contain brief, localized pauses, and that the story of Earth's earliest oceans may begin slightly earlier and in a slightly more complicated way than a simple single moment of global cooling would suggest. Let us take stock of this chapter. For roughly 500 million years after Earth's core finished forming and its moon rose into the sky, our planet remained a place defined by ongoing catastrophe. Debris from the outer solar system, possibly concentrated into a dramatic renewed wave by the gravitational rearrangement of the giant planets, continued to strike its surface. Its interior, still furiously hot, kept driving volcanic activity across much of the globe, continuously destroying and rebuilding the crust. And above it all sat a thick, likely ash-choked atmosphere of carbon dioxide, nitrogen, water vapor, and trace methane, poisonous by our standards, and almost entirely without the oxygen that we, and every animal we will eventually meet in this series, depend on to breathe. And yet even here, in what remains one of the most hostile chapters in this planet's entire history, we have found a hint, small, contested, and genuinely uncertain but real, that somewhere briefly conditions may have existed for liquid water to exist. That hint matters enormously because liquid water is, as far as we currently understand, an essential ingredient for everything that follows in this story. Not yet a full ocean, not yet anything stable, but a beginning glimpsed faintly in the chemistry of a handful of microscopic crystals, 4 1/3 billion years old. The bombardment was not yet over. The volcanoes were not yet quiet. But somewhere in this violence, water, however briefly, however locally, may have already been waiting. That is where we go next. Thank you so much for watching. If you found this video helpful, please support us by subscribing to the channel and sharing it with your friends and family. Every like, subscription, and share helps us create more videos like this. From all of us at Team Alex, thank you again for your support. We'll see you in the next video.